In the Explore activity for this lesson, it has us using some geometry software. So it looks like they are using Geometer Sketchpad, but I'm going to use GeoGebra because GeoGebra is what we have in the classroom and GeoGebra is free. So it says draw a triangle, label it ABC, and draw a point P so that we can rotate triangle ABC around point P. So in part B, it tells us to rotate that triangle around point P, and then it wants us to change the size, shape, and location of ABC and see how A prime, B prime, C prime changes. So I select in this pull-down menu the rotate around a point option. I select the triangle and then the point I'm going to rotate it around, and then it gives me a pop-up for how do I want to rotate it. I want to rotate it 90 degrees counterclockwise, and there it is. So if I move points around, if I move B, notice how B prime is moving. A prime moves when A moves. C prime moves when C moves. If I move this whole triangle, well, now it's not letting me. So it's not going to let me grab the whole triangle, but you kind of get the idea of what's happening. The next thing they want me to do is to measure the angle AP A prime, and then BP B prime, CP C prime, and compare those angle measures. So here I'm measuring angle A, P, A prime. Oh, it's 90 degrees. B, P, B prime. Look, that's also 90 degrees. And finally C, P, C prime, and they're all 90 degrees. Now what happens if I move point A? Look at these angles. Point B, and point C. No matter what, that angle is always the same, 90 degrees. So it is, all of them are 90 degrees, and they do not change as points are moved around. Measure the distance from A to P and A prime to P. What do we notice? Okay. So I'm going to make a segment from P to A and P to A prime, and it called them I and J. Notice that they're the same length. What happens if I move point P? Well, value changes, but they're still equal to each other. They are the same distance, and this doesn't change as P is moved. Does it change when I change the shape of triangle ABC? Again, the value changed, but the relationship did not. What can we conclude about the distance of a point and its image from the center of rotation? A point and its image are equidistant from the center of rotation. And if that word is kind of strange to you, think about the parts of it. Equi, as in equal, and distant, as in distance. They are the same distance from the center of rotation. What are the advantages of using geometry software as opposed to tracing paper or a protractor to investigate rotations? It's a lot faster. Plus, you kind of avoid a little bit of that human error that can happen when you're using a protractor and a ruler. So this is what it looks like when you are using a protractor and a ruler to do a rotation, which I am absolutely not going to ask you to do, but I want you to see what it looks like. So by definition, a rotation is a transformation around a point P, the center of rotation, such that the following is true. Every point and its image are the same distance from P, we already talked about that, and all angles with vertex P formed by a point and its image have the same measure. And we call that angle the angle of rotation. So in example 1, part A, they're doing a counterclockwise rotation of 150 degrees of this triangle around the point P. So the first thing they did is draw the segment PA. And then using a protractor, they made a 150-degree angle with PA. And then they use a ruler to mark a point A prime on this ray so that from P to A prime is equal to P to A prime. And then they repeat those steps for B and C, connect the dots, and there's triangle A prime, B prime, C prime. In the coordinate plane is where most of the rotations that we will be doing is where we'll be doing them. So here are the rules for rotations around the origin in the coordinate plane. If I'm doing a 90-degree rotation, and for our purposes in this class, notice how it says when no direction is specified, you can assume that a rotation is counterclockwise. So if they just tell you 90 degrees, then that means it's 90 degrees counterclockwise. Okay, so if I'm rotating 90 degrees counterclockwise, you're going to see that the numbers are switching places and the y-coordinate changes sign when it becomes the x-coordinate. 180-degree rotation is really easy to memorize. You're just changing the sign of the x, changing the sign of the y. You could think of a 270-degree rotation as a 180-degree rotation of this. Notice how these signs are opposites. But I know how hard it is to memorize a whole bunch of stuff. So one thing that you'll see me do in class when we're talking about rotations is you can physically take your piece of paper and rotate it 90 degrees, 180 degrees, 270 degrees, see where the new location of that point is, and that's the image of the rotated point. So here, they're doing a rotation of 270 degrees. They're using the fact that the rule is xy becomes y comma negative x. They wrote down all the coordinates of the original point, and then they applied the rule. They predicted the quadrant in which the image would lie, and notice how the pre-image was in quadrant 1. If I'm rotating it 270 degrees, it would be here after 90, here after 180, and therefore here after 270 degrees. And then they plotted it, and that's it. In part B, we're kind of doing the same thing, a little bit more on our own. So in part B, the rotation of x comma y is negative x, negative y, because we're rotating it 180 degrees. Find the coordinates of the vertices of the image. So they located k at 2 comma negative 1, L at 4 comma negative 1, and M at 1 comma negative 4. So now we just apply the rule. K prime will be at negative 2 comma positive 1. L prime will be at negative 4 comma positive 1. and m prime will be at -1, positive 4. Predict the quadrant in which the image will lie. Since KLM lies in quadrant 4, and the triangle is rotated by 180 degrees, the image will lie in quadrant 2. Plot K prime, L prime, M prime to graph the image. So K prime is at -2, 1. L prime at -4, 1. And M prime at -1, 4. And when I connect the dots, if I could draw, there's my 180-degree rotation. Suppose I rotate quadrilateral ABCD in part A by 810 degrees. In which quadrant will the image lie? 810 degrees, wow, that's a big number. What I hope you'd notice is that back here, when they gave us the rule, a 360-degree rotation just lands us in the exact same place. So let's figure out how many 360s there are in, I believe it was 810. Okay, so 810 divided by 360 is 2.25. So there's 2 full 360s inside of 810. So let's write this work out. 810 divided by 360 was 2.25. So if I do 810 minus 2 times 360, that's going to tell me what an 810-degree rotation is equivalent to. So 810 minus 2 times 360 is 720. That's a 90-degree rotation. So in part A, that quadrilateral was in quadrant 1. So if I do a 90-degree rotation of something that's in quadrant 1, it's going to land in quadrant 2. In the Your Turn example 7, it's asking us to rotate triangle PQR 90 degrees. The rule for a 90-degree rotation is that x, y will become -y, x. So what are the coordinates of P, Q, and R? P is at 2, 1, Q at 4, 1, and R at 4, -3. So that means when I apply the rule, that P prime will be located at -1, 2, Q prime at -1, 4, and R prime at 3, 4. So let's plot that. P prime at -1, 2, Q prime at -1, 4, and R prime at 3, 4. And there's our rotation. In example 3, a rotation has already taken place, but they're asking us to find the angle of the rotation. So in part A, the example is done for us. Look at what they did. They drew a segment from P to a point, and then from P to its image. So they drew segment PA, and then they drew segment PA prime. They used a protractor, and they measured the angle. Therefore, the angle of the rotation is 80 degrees, and it was counterclockwise. Part B, we're doing the exact same thing. So let me get a couple of tools from my program. I'm going to need a protractor, and I'm going to need a segment tool. So I'm going to draw a segment from P to Q prime and from P to Q. And then I'm going to measure that angle. And it looks like it's 130 degrees. And it went clockwise. So 100, what did I say? 130 clockwise. Doesn't matter which points you choose when you draw segments from the center of rotation to points of the pre-image and image. No, the angle of rotation would be the same for any of the points in the rotation. In part A is a different angle of rotation and direction possible. All right, part A, what are they referring to? Okay, absolutely. They counted the direction going this way, but could I have said that the rotation was a clockwise rotation of a much bigger angle? Yes. What would that angle be? It would be 360 minus this 80.